Hello, and welcome to the lecture on Chapter 6 of Astronomy Today. All right, so what are we talking about? Well, today we're finally introducing the solar system. Okay, now that is honestly the content of this entire semester, with a little bit of introductory chapters out of the way. However, this is the chapter where we kind of lay the basics of the solar system, and then we'll talk about more details about individual planets and such later on. Okay, so what do we want to do in this introductory chapter? Well, we want to talk about an inventory. So what is the solar system? What does it consist of? We want to measure the planets, talk about measuring them, talk about the overall trends, right? What's the overall look of the solar system? Okay, that's the layout. Then the big thing, what's the difference between terrestrial, like the planet we live on, and Jovian planets? Okay, then we'll talk a little bit about a particularly cool idea called a gravitational slingshot. And then finally, interplanetary matter, everything between the planets. Okay, so let's get to it. So how did the solar system form? Okay, that's going to be the second to last section here. We're also going to talk about spacecraft exploration of the solar system and a little math section here on angular momentum, because angular momentum is important to understand that story about how the solar system formed. And then Jovian planets, okay, the planets like we don't live on, and planetary debris. How are they connected? Okay, so early astronomy knew the following objects in the sky, the so-called wandering stars, the things that behaved differently than any other object in the sky. That was, of course, the moon, all right? The stars, the background, all the objects in the sky that remained fixed relative to each other. Mercury, another one of the wanderers, Venus, Mars, Jupiter, Saturn, and we were aware of comets because we would see comets' tails, ancient peoples would, and meteors, like meteor showers. Okay? All right. So now what do we know? Well, now we know that the solar system has more than 169 moons. Okay? One star, our sun is an example of a star, pretty normal star, 8 planets, okay? Because ancient astronomers had no idea that Uranus or Neptune existed. Okay, now Uranus is just barely not visible with the naked eye. You need a very rudimentary telescope to discover it. So it would have been discovered early after the invention of telescopes. Neptune, on the other hand, is very difficult to see. It's very faint. Okay, so you need a high-powered telescope to see Neptune. Okay, we have 8 asteroids, more than 100 Kuiper Belt objects, more than 300 kilometers in diameter, and many small asteroids. Okay, so what we're saying by that, there's not only 8 asteroids total, but there are 8 asteroids that are greater than 300 kilometers. So there's 8 major asteroids. Okay, all the asteroids are in the asteroid belt. The biggest asteroid and the only one that's considered a dwarf planet is named Sirius, but there's others of these major asteroids. Okay, we'll talk about the asteroid belt later on. And as far as the fact that there are 100 Kuiper Belt objects that are greater than 300 kilometers, what does that mean? What's the Kuiper Belt? Well, the Kuiper Belt is the very edge of the known solar system, and that includes Pluto. Okay, Pluto, which used to be considered a planet, but then when other objects that were equivalent to Pluto in size and mass were discovered, instead of adding those to the list of planets, they were classified together as Kuiper Belt objects. Okay, also called dwarf planets. And many, many small asteroids, thousands of smaller asteroids, comets, and meteoroids. Okay? Now, additionally, we've discovered over 800, and that number is quickly growing, extrasolar planets. So these are planets around other stars, including our closest neighboring star, Alpha Centauri, which is actually a triple star system with Alpha Centauri A, Alpha Centauri B, and Alpha Proxima. So those 3 stars together orbit each other and have planets that orbit the 3 of them. Additionally, we found particularly good solar systems that have lots of planets. Now we're continually adding to that list and kind of discovering the types of planets that other stars have. But the point being, there are a lot of these extrasolar planets. All right, we don't see them directly, almost never, but we do see the evidence of them as they tug on the star or they affect the colors of the light coming from the star. Okay? And this has helped us understand planetary formation in our own solar system. All right, so what do we mean when we're talking about measuring the planets? Well, we need to know the distance from the sun, and we know that from Kepler's laws. Okay, so we know that there's a relationship between the period and the radius of the orbit of the star, okay? Particularly Kepler's third law, okay? The orbital period can be directly observed, okay? So the orbital period, we don't need any formula. We can just count, observe how long it takes with telescopes for that planet to go around the sun, okay? The radius we can measure if we know the distance, okay? So if we know the angular size, how much space that planet takes up, say in a telescope, and maybe it's a few arc seconds of angular size, then we can convert that with a known distance to a radius, okay? So combining a known distance with a known angular size gives us radius. Now we can also calculate a mass from Newton's laws. The best way to calculate a mass of the planet is to observe the behavior of moons around that planet, okay? It can be tiny, but the planet needs to have some moon around it in order for us to observe its mass. Now, are there exceptions? Yes. For example, Mercury has no moon, but we can still measure its mass based on its orbit around the sun. Now, it's better to measure the mass based on the orbit of a moon around that planet, but sometimes that's not possible, okay? Rotational period, directly from observation. Rotational period would mean like the equivalent of a day, how long it takes that planet to spin on its own axis, and the density. Because once we know the radius and we know the mass, then we can combine that information together to calculate the density. Because density is just mass per volume, okay? And if we assume the planet to be spherical, a very reasonable assumption, then we can use that radius formula for the volume of a sphere and get the density. Densities vary, okay? You'll see that they group together between the terrestrial planet densities and the Jovian planet densities. Okay, so here's all that information all in one table. There's a lot to take in here, right? I could spend a half hour just talking about kind of interesting facts on this table, but we can just see that here are the planets, here are all the criteria that we mentioned, and I would highly recommend that you kind of look through this and think about these quantities. What do they tell you? How much bigger is Jupiter compared to Mercury? How much bigger is Saturn compared to Earth? How long is a day on Saturn? How long is a year on Saturn? How long is a day on Neptune? How long is a day on Uranus? Like kind of look at the numbers, see if there's anything interesting that shows up, okay? All right, so the overall layout of the solar system is such, okay? So all the orbits but Mercury are close to the same plane, okay? So if you look here, this is like a side view of the solar system right here. From a side view of the solar system, you can see that there's very little angular spread in terms of the planets. It really, if you see like a model of the solar system, you'll usually see it represented as a plane and all the planets, kind of like laid on that plane. Well, it's actually close to the reality. The planets really are on a plane. Now, there's a physical explanation for that. It's not just amazingly convenient. There really is a reason for it. But Mercury, very close, very affected by the gravitational effects of the sun. Mercury has the most shifted of all the orbits. Even then, it's not shifted that much. Okay, it's not like the orbit of Mercury is like going around like this or something. No planets do that. Okay, they're all essentially on a plane with some deviation. In particular, Mercury's deviation from that plane. Okay. So looking, we can also see that the terrestrial planets, let me go ahead and zoom in on this. Look, the terrestrial planets are really clustered in here, right? This is Mars' orbit right here, which is the furthest distant from the sun of all the terrestrial planets. Then we have this asteroid belt, which is represented by this blurry section around kind of outside of the Martian orbit and inside of Jupiter's orbit. So in other words, the asteroid belt is between the orbit of Mars and the orbit of Jupiter. Now, Jupiter's not that much further out than the terrestrial planets, but it is significantly further, right? It's about twice the distance that Mars is from the sun, Jupiter's average distance from the sun. Okay, and then we have a big jump until we get to Saturn. So now the distances between the planets grows. Because again, right, lots of clustering with Mercury, Venus, Earth, and Mars. But then distance between Saturn and Jupiter, not so much, right? They're spread apart. And then to get to the orbit of Uranus, that one that was not observed by ancient astronomers, it's further still. And then Neptune is another big gap. So as we get further out in the system, the planets first become bigger because the Uranus, Saturn, Jupiter, and Neptune are all massive planets, and they're much further apart, okay? And then finally, outside of the orbit of Neptune, excuse me, is the Kuiper belt, okay? So in terms of belts, we got the asteroid belt and the Kuiper belt, okay? Both composed of many, many small objects and dwarf planets, okay? All right. Because the planets' orbits are close to being in a plane, as we just mentioned, it is possible for them to appear in a straight line as viewed from Earth, right? So we can really, if you look into the sky, you can really kind of see that straight line that connects the planets. And it makes it kind of easy if you see a bright star and you suspect that that star is so bright that it might be a planet, because often the brightest star you see in the night sky is not in fact a star, but is in fact a planet. You can kind of follow a line of sight and find other bright quote unquote stars and realize that those are other planets and they're along the ecliptic. Okay? Now they're along the ecliptic because the ecliptic is the path that the sun appears to take through Earth's sky, right? Over the duration of the year. Well, same thing here. Okay? The planets appear on that same path. Now they don't appear when the sun is in the sky because they'd be washed out by the bright light of the sun, but at night they're along that same path. Okay? So in this picture of the 8 planets and the sun, the differences between the 4 terrestrial and the 4 Jovian planets are clear. Now I want to specifically, I've kind of been hinting at it, but I want to specifically call attention to that term Jovian planet. So these are the 4 Jovian planets, okay? Jovian planets. And then the terrestrial planets are these 4, okay? Now, Earth's moon is thrown in there because it's so important from our perspective, but obviously it's not important from the Martian perspective or something, right? It just happens to be our moon, right? But again, special to us, so we always have that Earth-centric view. But these 4 are the terrestrial planets. Okay, so by terrestrial we mean rocky, and by Jovian we mean gassy. Okay, or gaseous. Okay, so that's the big difference. Is the Jovian planets are the gas giants because look, they are giant. Look at, I mean, this is 2 scale. Okay, and then the terrestrial planets are smaller, denser, and rocky. Okay, all right. We live on one of the terrestrial planets. Now, also notice, look how massive the sun is. Right, all of the planets pale in comparison to the size of the sun. Now, Jupiter is the closest, right? Jupiter is an appreciable fraction of the size of the sun, but it's still much, much smaller, okay? All right. So the terrestrial planets, Mercury, Venus, Earth, Mars, all close to the sun, all interior of the asteroid belt. Jovian planets, Jupiter, Saturn, Uranus, Neptune. That's it. There are 8 planets, 4 of each, okay? The terrestrial planets are small and rocky, close to the sun. They rotate slowly, all right? They have weak magnetic fields, few moons, and no rings. Okay, as far as weak magnetic fields, that's true. Earth by far has the strongest of all the terrestrial planets' magnetic fields by far, which is great because it harbors life, okay? But it doesn't compare to the huge magnetic fields that we see like in Jupiter or even the other gas planets, all right? The Jovian planets are large, gaseous, far from the sun. They rotate quickly, right? So they have very fast speeds. They have strong magnetic fields, many moons, and they all have rings. Okay. Now you might be like, wait, they all have rings, right? Jupiter here isn't even shown with a ring. Uranus and Neptune ring aren't particularly bright or particularly reflective, but they're all there. Jupiter's ring only shows up in the infrared because it's so dusty and it's so dark that it doesn't really reflect any light in the visible spectrum, but it does show up in the infrared. Saturn is just by far like the cleanest, brightest of all of them, so it's the most dramatic. Okay? So, the differences among the terrestrial planets. Well, they all have atmospheres, but they are very different, okay? The surface conditions vary as well. So there's really a dramatic story to tell about the differences between the planets, the terrestrial planets. Only Earth has oxygen in its atmosphere and liquid water on surface, okay? Now there's some frozen water on Mars, but that's it, okay? There's no liquid water on any of the other 3 terrestrial planets. Earth and Mars spin at about the same rate, so a day on Mars is about the same as a day on Earth, okay? Very, very similar. Mercury, however, is much slower. It's about 60 Earth days, okay? And Venus is so slow. Venus is about an Earth year to take a full day. Venus is incredibly sluggish in its rotation, very strange, okay? Only Earth and Mars have moons. Mars just really has some tiny moons, okay? And only Earth and Mercury have magnetic fields. And Mercury's magnetic field is incredibly weak, all right? So if you kind of notice something, is that Earth definitely is the standout from the 4. Now, to be fair, maybe 3 billion years ago, Earth was more similar to the other planets, but they've taken different paths due to subtly different conditions. And this is based on our best understanding, okay? So here's a little side note, discovery, okay? Gravitational slingshots, what the heck is that? Well, a gravitational slingshot can change the direction of a spacecraft and accelerate it. So the idea is a spacecraft flies close to a planet and then departs with a greater velocity. All right. So you basically, if you're an engineer planning the trajectory of a space probe that you want to go into the distant reaches of the solar system or perhaps permanently leave the solar system, then you might have it so it flies close to, say, Jupiter, okay, which is in fact the planet shown here. And if it does that, if it passes fairly close to Jupiter on its way out to the edges of the solar system, then it will pick up velocity. What happens is it steals a little bit of momentum from the planet, but not so much to affect its orbit, because after all, this is a tiny probe and a massive planet. But it steals a little bit of momentum from the planet, and that causes a big increase in its velocity. Okay, so a very popular technique of getting space probes out to the distant solar system. Because sometimes it's just the energy requirements to give the space probe enough initial velocity, a great enough starting speed, are just too much. We don't have enough fuel to do that. Or can pack enough fuel in a small enough package to do that on the space probe. So it makes more sense to have a space probe slingshot once, twice, or even 3 or more times as it goes out into the solar system. But of course, you have to plan that so its trajectory passes near planets as it moves out through the solar system. Okay? Which means timing is very important. Okay, so on to interplanetary matter. So the asteroids and the meteoroids have rocky composition. Okay, asteroids are bigger than the meteoroids. Okay, here's one of the most massive of the asteroids, Vesta, right? One of those 8 that's greater than 300 kilometers. Vesta is about 500 kilometers across. Vesta is not big enough to be spherical, so it's not considered a dwarf planet. It's kind of potato shaped, as you can see. Okay, but it is massive, right? 500 kilometers. That's a big chunk of rock. Okay, it's there's some microgravity there. Like if you were on the surface of Vesta, you would notice everything drifts down at a few centimeters per second. It's not like on Earth where things fall at many meters per second, but things drift down. Right, there would be noticeable gravity, although very small. Okay, but point being is this is a large asteroid, and also point being asteroids and meteoroids are rocky. Okay, remember that. Okay. On the other hand, comets are icy. Okay, now they often have rocky cores, so they're kind of like dirty snowballs. There's rocks mixed in there, but they tend to be bigger than asteroids, and they're mostly ice, okay, because there's more ice. So the ice is just more common where comets are formed, thus it outweighs the small amount of rock that composes an average comet, okay? So comets are dirty snowballs, mostly ice. Now, it's not entirely water ice. It can be other hydrogen compounds, but it's all kind of ice, right? It can be frozen methane, frozen ammonia, but definitely some H2O is in there as well. Okay, so that's the idea. They're icy. So that's a big difference between comets and asteroids. All right. Pluto, which was once classified as one of the major planets, right, is the closest of the large Kuiper Belt objects. Okay, that's why it was discovered first, and it took some time until the other major Kuiper Belt objects were discovered. But there are some that are in fact more massive or have a greater radius than Pluto. So Pluto's only really special in that it's the closest. Okay, but it's outside of Neptune's orbit. It is part of the Kuiper Belt. All right. So as far as exploration of the solar system, so here we have a Soviet probe called Venera, which landed on Venus, okay, from 1970 to 1978, and probes, because it was a series of them. The individual probes did not last that long. Venus has very hostile surface conditions. We'll talk about that in our whole chapter where we dive into Venus, and it certainly is quite interesting and quite dramatic. But subsequent probes landed and were able to acquire some data before they melted, okay? The most recent Venus expedition from the United States was the Magellan Orbiter, okay, which didn't land, but was able to collect a lot of data, and it orbited from 1990 to 1994, okay? So orbiting around Venus, trying to use certain cameras to pierce Venus's incredibly thick atmosphere, because Venus does have an atmosphere, but it's a very hostile atmosphere, and so dense, so much denser in our atmosphere, and very almost completely opaque, but you can look through it in the infrared and other frequencies, okay? Now, we haven't just gone to Venus, not at all, right? We've certainly gone to Mars. Here's Viking that went in 1976, right? A Viking probe landed on the surface of Mars. And you might have heard about Mars in the news just recently because we had Perseverance, the newest and most sophisticated of the Martian probes, land on the surface of Venus. And it's a rover. And it's a rover that has a helicopter. So we've come a long way since 1976 on the things that were landing on Mars. Okay? Here's Spirit, which landed in 2005. This was part of the kind of the generation of space probes and space rovers, or Martian probes and Martian rovers, that led up to Perseverance, that just landed recently, about a week before my recording of this lecture. Point being is that Spirit is much more sophisticated, high quality cameras, right? Able to move around, do science experiments on board. But even that, right, in the 15 years since Spirit, we've had major innovations in our Martian rovers, okay? In addition to sending rovers and probes to Venus and Mars, we've set a couple of space probes on trajectories that will permanently send them out of the solar system. Pioneer and Voyager are examples of that. These are space probes that have taken advantage of that gravitational slingshot and are on their way to leave the solar system and never return. Okay? Cassini was a space mission that went to Saturn, okay? It arrived in 2004 and has returned many spectacular images, okay? So it spent quite a bit of time once it got there from 2004, continuing to orbit around Saturn, using a leftover fuel to use thrust to take it on trajectories around some of Saturn's moons as well, such as Enceladus, which we'll talk about in our chapter on Saturn. But point being, was a very successful mission before it eventually ran out of fuel and concluded its mission by crashing into the upper atmosphere of Saturn and burning up. Okay. All right. So many fascinating things that these scientists do by sending space probes out into the solar system. But has it helped us understand how the solar system formed? Yes. And so has our study of those exoplanets that we mentioned. So we have a pretty good model now, right? It's, of course, it will continue to get refined over the decades and centuries to come, but we have a pretty good model about how the solar system formed. And it has to do with something called nebular contraction. That's really the first step. So a cloud of gas and dust contracts due to gravity. Conservation of angular momentum means it spins faster and faster as it contracts. It's like an ice skater that has their arms out and then pulls their arms in, and as they do so, they spin faster. So too does this giant cloud of dust spin faster as it contracts, and also as it contracts and becomes denser, it heats up. Eventually, the center of it heats up so much that it heats up hot enough to start nuclear fusion, and a star is born. And the leftover remnants, the things that didn't collapse into the star, well, they eventually form the planets. The planets like our Earth and Jupiter and so on, right? All 8 of them, okay? So conservation of angular momentum says that the product of the radius and the rotation rate must be constant, okay? So it's R times omega, R1, omega 1, equals R2 times omega 2, okay? Omega is the rotation rate, which is measured in either degrees or radians per second. Okay, so degrees per second. So it's not like a velocity exactly, which would be distance per second, like meters per second. Instead, it's angle per second. It's angular change. So if you're making a complete rotation every second, you'd be covering 360 degrees per second. That'd be 1 rotation per second. Okay? And then R is just the radius. And R would be measured in meters. Okay? Radius. Good. So as things become smaller, they spin faster. That's conservation of angular momentum. It's one of the major conservation laws in physics. Energy is conserved, momentum is conserved. Also, angular momentum is conserved. All right? So nebular contraction is followed by condensation around dust grains known to exist in interstellar clouds, right? So this dust has been studied outside of our own solar system extensively. All right? This is an example of that dust. The accretion just means gathering together, then leads to larger and larger clumps. Finally, gravitational contraction takes over and planets form. So there's this natural process that things bump into each other and they stick together. They don't have enough energy to just ricochet off of each other. So then 2 dust grains that were independent come together and then they stick to form one new bigger dust grain. So that's a natural process that's occurring. And then that process eventually leads to gravity pulling in even more matter. So it's just this gravitational kind of, like continuing along process. Okay? So terrestrial, in other words, rocky planets form near the sun. This is due to one thing, high temperature. Okay? Because nothing else can form there. Near the sun, inside something called the frost line, there's no ice. okay? Any hydrogen compounds that would exist in space are hot enough to boil, and thus they can't, they're in a gaseous form, so they can't easily condense. Now you might think, well, isn't space really cold? Well, it's really low pressure also. So the small amount of heat energy that does exist in space, between the planets, right, that exist now, right, but that we're forming at this time. Well, but all that empty space between the planets, although it's might seem cold to us, there's quite a bit of radiative energy coming from the sun and plenty to boil hydrogen compounds at the very low pressure that exists. Okay, it's not a perfect vacuum, but it's pretty close to a vacuum. That's what I mean by very low pressure. Okay, all right. So terrestrial planets, nothing else can form. So the only thing that's out there is rock. So you're just left with rock. But there's not that much rock. Okay, there never were that many heavy elements to begin with. Heavy elements are only born in the cores of giant stars. So in the 13 billion year history of the universe, there hasn't been that much rock that's ever formed. So that's why the terrestrial planets are smaller, because there's not as much rock to go around. Okay? All right. So T-Tauri stars are in highly active phase of their evolution and have strong solar winds. These winds sweep away the gas disk, leaving the planetesimals and gas giants. Okay, and that was a phase that our own star went through, and ours apparently was particularly active, and so it sweeps away all the leftover matter. So essentially, the planets have a couple 100 million year window to form before most of the gas is pushed away, and that formation phase of the solar system comes to a permanent end. Okay? So the Jovian planets, well, once they were large enough, may have captured gas from the contracting nebula. Okay, so that's the thing, is the Jovian planets are so large that they seem to have not just collected ice, but actually to have collected gas as well, things that never actually froze because of that gravitational force. Or they may not have formed from accretion at all, and may directly form from instabilities in the outer cool regions of the nebula. So there's actually more complex models and more unanswered questions in terms of the formation of the Jovian planets, because they're a little bit too big to have a simple explanation like the terrestrial planets. Okay? So detailed information about the cores of the Jovian planets should help us distinguish between the two possibilities. Okay? It's also possible that the Jovian planets may have formed further from the sun and migrated inward. Okay, so and because we see that in other solar systems, we see a lot of evidence of inward migration of gas giants, including to forming these things called hot Jupiters, where you have planets the size of Jupiter that have migrated so close to their star that they're essentially in orbits like our Mercury, which is really dramatic, right? To have a planet that large but that close to the sun. And that appears to be due to a migration and kind of an energy process where that planet moves closer and closer to the star. And perhaps that happened in our own solar system, but they only moved as close as we see them today. Okay, so the asteroid belt, okay, well, this orbits mostly between Mars and Jupiter. There's a bit of the asteroid belt that actually orbits in the orbit of Jupiter called the Trojan asteroids. Jupiter's gravity kept them from condensing into a planet or accreting into an existing one, onto an existing one. Fragments left over from the initial formation of the solar system. That's what the asteroid belt is. So in other words, there would be another planet there, except Jupiter prevented it from forming. Okay, so there's a push and pull from Jupiter, and it causes the asteroids to never be able to form a planet. So Jupiter is directly responsible for the asteroid belt existing. Okay, so the general timeline of the solar system can be shown like this. All right, so we have a dramatic first million years, then 10 million years, then 100 million years, and then a billion years. Solar system is about 4.5 billion years old. Okay, and we can see that there was kind of these intense phases that didn't last very long early on, and then finally we have asteroid belt and Kuiper belt forming after the planets started to form. Okay, so icy planetesimals far from the sun were ejected into distant orbits by gravitational interactions, kind of like the gravitational slingshot that engineers plan for when they send space probes out into the solar system. But this would have happened naturally, okay? And this then formed the Kuiper belt and the Oort cloud. So these were leftover chunks that never joined with the gas giants, but then got flung out of the solar system. Now, we haven't mentioned the Oort cloud, but the Oort cloud has never been confirmed to exist, but there's a lot of suggestion that it does exist. And essentially, it's the very edge of the solar system. And it actually is spherical, unlike everything else that's on a plane, because even including the Kuiper Belt is on that plane that we mentioned, right? All the planets, the asteroid belt and the Kuiper Belt, all essentially on that plane of the solar system. Well, the Oort cloud is the very edge, some 10,000 times further than the Kuiper Belt, so much, much further. Hence, it's never been directly imaged. And that Oort cloud is entirely a sphere, and it's where most of the comets are thought to exist. But there are also quite a few comets that exist in the Kuiper Belt, okay? Now, some of these icy planetesimals didn't get flung out, but instead were captured by the gas giants and became the moons of the gas giants. Okay, so many of the moons of the gas giants, the moons of Jupiter, the moons of Saturn, the moons of Neptune, the moons of Uranus, those are captured comets. Okay, all right. So Kuiper Belt objects have been detected from Earth. A few are as large or larger than Pluto, hence Pluto's demotion from a major planet, and their composition appears similar, because Pluto has a composition that is very much like a giant comet. It's mostly ice. Okay, about 1/3 of all Kuiper Belt objects, including Pluto, have orbits that are 3-2 resonance with Neptune. Okay, these are called plutinos. All right. Okay, so here's the summary. The solar system consists of the sun and everything orbiting it. That's what we mean by the solar system, okay? And the sun, by the way, is 98% of the matter in the solar system, okay? The asteroids are rocky and mostly orbit between the orbits of Mars and Jupiter, okay? Comets are icy and are believed to have formed early in the solar system's life. Major planets orbit the sun in the same sense, and all but Venus rotate in that sense as well, okay? So they all spin in the same direction. Venus is upside down for some reason. The planetary orbits lie almost in the same plane as you mentioned. Mercury is the greatest deviation from that plane, and even it is fairly planar. Okay. The 4 inner planets are known as the terrestrial planets. They're rocky, small, and dense. Okay, because there were no ice there to contribute to their size. The 4 outer planets, the gas giants, are the Jovian planets. Okay, they're gaseous and large. The nebular theory of the solar system formation says that a cloud of gas and dust gradually collapsed under its own gravity, spinning faster and faster as it shrank. Okay, the condensation theory says dust grains acted as condensation nuclei, beginning the formation of larger objects. The solar system is orderly, not random. Okay, we need formation theory to explain this. The condensation theory is the current favorite. Large clouds of interstellar gas and dust start to collapse. The sun forms at the center, and the dust particles act as accretion nuclei to form the planets. The rocky planets would form close to the sun. The outer planets contain material that would vaporize or escape at higher temperatures. The Jovian planets may have formed directly from instabilities in the cloud, okay? And the asteroids never condensed into larger objects. They're leftovers. So both comets and asteroids are leftovers, okay? And really, you can think of asteroids being like the terrestrial leftovers and comets being the icy leftovers, okay? Leftover planetesimals, the bigger ones, were ejected from the main solar system and now are in the Kuiper Belt and the Oort cloud. Some occasionally get pulled into the inner solar system. That's why we have comets that only come every few hundred years, okay? They take these very, very long eccentric orbits. And as I mentioned before, some ended up being the moons of the Jovian planets. Okay, so I hope this brief introduction to the solar system has been interesting and informative. Thank you so much for watching.